This video provides a general introduction to the AC node equations tutorial in Circuit Tutor, and in particular we'll show you how to work problems at level 1. AC node equations is very similar to the DC node equations tutorial that you may have worked previously. And in fact, you might even want to watch that video for further details about how to use it. So I'm mainly going to highlight the differences from the DC case here. So I'll click on the video, and as you can see we have 4 different levels here, similar to the DC case. So let's look at an easy level problem. Now, as always, we can show examples here, and this will show basically how to work a problem in the phasor domain. So you're writing equations here in the phasor domain where the impedances of the capacitors and inductors have already been converted to the phasor domain for you. Initially, in a problem like this, you would have to do that conversion as you did in the impedance simplification game. But in this case, the conversions have already been done, and you basically just need to write the KCL equations and the other types of equations that are involved. So let's work an exercise at the easy level. And the first thing we would need to do, just as in the DC case, is to place our reference node or our ground. So I'm going to select that as being the bottom node, since that has a lot of connections. And then we do get some instructions. And again, the instructions are generally similar to the DC case. And now we would simply need to write the appropriate types of equations. So in this case, we don't have any voltage sources that would apply voltage constraints. So we basically just need to write KCL equations and sought variable equations. And as in the DC case, we want to make sure that we don't combine elements in series when writing these equations. So let's write an equation, for example, for node 1. And we need to sum all of the AC currents leaving node 1 to other nodes and set that equal to 0 by virtue of KCL. So we first of all need a term like this. And then for this current going from V1 to V2, we'll need this type of term. And that's the only currents exiting that node. So that would be equal to 0. And then I will just use the tab key and fill in the values here. So this is V1 divided by 7 ohms. And then this would be V1 minus V2, in this case divided by J2 ohms. Now I can enter complex numbers in any format that I like. It is possible to use I instead of J, but electrical engineers normally use J to avoid confusion with current, which is I. And there's other notations that can be used, but this is probably the easiest thing to do, is just to type what's on the element. So we'll check that equation. That is correct. Let's write now a KCL equation for node 2. And so, for example, here we'll need a term for the current exiting from V2 to V1, and then a term for the current going through the current source. I'm sorry, that would be the wrong type. That would be this type. And then finally, the current through the capacitor. And so that would be a difference of node voltages, and that would all equal to 0. And so we would have V2 here minus V1 divided by J2 ohms, just as if that were a resistor, basically, using the relationship that says V equals IZ for an impedance. And then this current now is actually entering, so we're going to have a minus sign here. And we can't enter this as I2S, or I'm sorry, I1S, as it's noted in the circuit diagram. Instead, we need to go down and use the actual value, which would be 2 angle 0 amps. And so we fill that in as 2 angle 0 amps. And then the third current leaving node 2 to go to node 3 would be V2 minus V3 divided by minus J6 ohms. And that would be correct. And then we would need, let's see, another one for node 3. And that would have a term like this going through the capacitor, and then a term connected to ground, and then a current source term for I2S, and that would be equal to 0. And so we now have V2 minus V3. I'm sorry, did that wrong. That's V3 minus V2 divided by minus J6 ohms. And then we'd have the current going this way, which would just be V3 divided by 8 ohms. And this current is actually exiting, so that is in fact the current leaving, so it'll have a plus sign. And so I2S, the value is 9 angle 120 degrees. So we'd put 9 angle 120. And that would be correct. And then we need to write SOT variable equations for the SOT voltage and current. So we'll select a SOT branch voltage here for V0. And we'll say that V0 is equal to, so V0 is right here, so that we see that since the negative side of V0 is ground, V0 is just going to be the same as V3. And then we need a SOT branch current for I0. So we'll say I0. Now we're going to use an Ohm's law type of relationship. And I0, let's see, is right here. And so that would be simply V1 divided by 7 ohms. Using, in this case, it's actually Ohm's law since it's a resistor. And we're all done. And we just say no more equations. And as always, we can show a detailed explanation if you wish to do that. And it'll cycle through and actually show you color coding the currents leaving each node and highlight the corresponding terms in the equation. So we'll just click through that. And that will summarize the problem. Thank you very much.